I'm going to talk about density, and this is one of the intensive properties of matter that was discussed on a previous video. There are three objectives we're going to cover today. The first one being able to calculate the density of a substance. The second one being using water displacement to calculate the volume and density of a substance. And the last objective today is to use density to identify a substance. So let's get started by just looking at the definition and the formula that's going to be used for this. So density is the mass to volume ratio of a substance, and it's usually going to be represented by the formula D equals m divided by V, or density is equal to mass divided by volume. And here on the screen you can kind of see that I have a little example problem here that shows if you were in a situation where the mass of the substance was 120 grams and it had a volume or took up 5 milliliters of space, then the density that would go along with that would be 24 grams per milliliter. The unit for density will always be a mass unit per a volume unit. The units are not extremely important, they will vary, but just make sure you take the mass unit that's given divided by the volume unit that's given. So let's look at our first example problem here. So this example problem says you have 500 grams of sugar and occupies a volume of 0.315 liters, and it wants to know what the density of the sugar is in grams per milliliter. Now, some things we got to be careful with here, and a lot of students will miss some of these details. Notice that we're given volume in liters, but we're asked for a density in grams per milliliter. So we're going to have to do a few unit conversions to make this work out for us. So to tackle this problem, you would use D equals m divided by V. Your mass would be 500 grams, that's given to us in the problem, and our volume is 0.315 liters. We're going to convert the volume into milliliters, and that's what I've done here. So I took 0.315 and multiplied it by 1,000 because 1 liter is equivalent to 1,000 milliliters. Now, once I've done this, now I can plug in my values to the formula. So I plug in my 500 grams and I divide it by my volume, which is in milliliters. And notice that I get my final answer, or my density value is 1.59 grams per milliliter. So a common mistake with this first example would be to forget to convert to milliliters. Let's look at a second example. This one's a little bit more difficult. So this one wants to know the density of pure solid copper. It's 8.94 grams per milliliter, and it wants to know what volume does 5 kilograms of copper occupy. Now right off the bat you should notice that I've got grams and kilograms in this problem, so there's going to have to be a unit conversion to make this work. So let's take a look at how you tackle this. Okay, so first thing you would need to do, you'll notice on all these problems I always write the formula first. So D equals m divided by V. Now my mass and the density value of 8.94, so that's 8.94 grams per 1 milliliter, needs to be switched to kilograms. So 1,000 grams is equal to 1 kilogram. So I took, and I'll kind of highlight this part here, draw an arrow to it so you can see what I'm talking about. I took 8.94 grams and divided it by 1,000, and that gives me 0.00894 kilograms. Now, once I have these values, now I can plug it into the formula. So this is my density, the same density that was given to me, except now it's in kilograms per milliliter. So that was the purpose of that previous step. So I've got my density, and then I plugged in my 5 kilograms, and then the whole purpose of this problem was to solve for V, or solve for volume. How many milliliters would this thing take up? And to do this particular problem, sometimes the algebra messes people up a little bit. But what I did mathematically was I took 5 kilograms divided by 0.00894 kilograms per milliliter, and I get 559 milliliters. So this one is a little bit harder of a problem than the first one we looked at. Okay. Let's take a look at water displacement. This is actually pretty easy to figure out, but it does require a little bit of lab skills because you're going to have to be reading, for the most part, a graduated cylinder for these types of problems. So in the box up here on the screen, it talks about a situation with a hammer, and it says, what is the density of this 2 kilogram hammer based on the illustration below? So they've already given us the mass for this problem, so we don't have to weigh the hammer or do any calculations for that. And they've given us an illustration that has a graduated cylinder, and it's showing in the first diagram that the hammer is not in the graduated cylinder yet. And before the hammer was placed in this graduated cylinder, we can use the meniscus to read the volume. Now the meniscus is going to be the curve in the bottom of the water. So what you'll do is you never read the graduated cylinder here. So you can kind of see how the top edges of the water are a little bit higher than the center. So you'll always read it at the curve in the meniscus at the bottom. I'll draw an arrow to kind of show this. So this is where I take my volume reading in a graduated cylinder. And we can see that the volume was 65 before the hammer was placed into the graduated cylinder. Now we're going to do the same thing with the after illustration, which shows the hammer is in the graduated cylinder. And we can see that the water level has changed again. And this time, and I'm actually going to move this arrow. Let me move this out of the way so we can read the increments here. So it's right there. Now what I can do is use the 70 mark and the 65 mark as reference, and I can count my way up from 65. So 65, 66, 67, 68, 69 is where the water is hitting. So this mark right here would be 69. So how do I solve this? It's actually pretty simple. I will take the final volume in the illustration on the right side, which was 69, and subtract the initial volume before the hammer was in the water, which was 65. So 69 minus 65 is 4 milliliters. So that's the water displacement. Now the amount that the water rises is actually the volume of the object you put in the water. So the hammer's volume is 4. So now we have the volume of the hammer and the mass of the hammer. So what we can do is apply our D equals m divided by v equation and plug in the 5 kilogram hammer divided by the 4 milliliters of volume it takes up, and we will reach an answer of 1.25. Oh, and that unit's not right. It should be 1.25 kilograms per milliliter, not just milliliters. So that's how you would do a water displacement problem. Now, the last thing I want to talk about is pretty simple. This could be something that comes up on some questions you might encounter. And I'm not going to go through the whole calculations again because we've done two or three examples of this already. But I just want to talk about what you would do. So let's say you were doing a density problem and you were able to solve for density using some of the skills we learned earlier in this video. And you get a value from it, and they might ask you, based on this value, what is the identity of the material? And most of the time they will give you a chart. So let's say that you did a calculation and you found the density of the object to be 2.65. Well, you might look over the chart and you might say, okay, 2.65, that's very close to aluminum. So then you could come to the conclusion that the particular metal in the problem must have been aluminum. So this is super common. I always include some of these on my exams as well, where students have to calculate the density from a word problem and then take it a step further by making an identification for that particular substance. So these are the most common styles of questions you will see with density. So hopefully this video has been helpful.